Hey there, I'm Benjamin, and today, as a continuation to my previous video, we shall cover two results that are immediate consequences of the monotone convergence theorem, which we discussed in our last video. Let's dive in. First, we have a lemma known as the Peppo-Levy's lemma, which states that if XMU is a measure space and Fn is an increasing sequence of non-negative measurable functions on the space X, and if the sequence of integrals, integral of f over x with respect to mu, is a bounded sequence, then Fn converges pointwise on X to a measurable function f that is finite almost everywhere on X. And furthermore, the limit of sequence of these integrals is exactly equal to the integral of the limiting function, and this value is a finite value. Let us look at its proof. We start by defining a function f such that fx is the limiting value of fnx and tends to infinity for each point x in the space X. Then, since each fn is non-negative, f must also be non-negative. Also, as we discussed in the previous video, f, by construction, being the limiting function of a sequence of measurable functions, must also be a measurable function. So, since we have an increasing sequence of non-negative measurable functions on X, which converges pointwise to a function f for each x in the space X, we can apply the monotone convergence theorem to get the first part of the inequality. The finite part is then quite simple to prove, since we were given that the sequence of integrals here is a bounded sequence, and we know for a fact that for any bounded sequence in the set of real numbers, if the limit exists, it must be a finite value. Finally, since f here is a non-negative measurable function on X, where the integral of f over x is found to be a finite value, by this result, f must be finite almost everywhere on X. So, in conclusion, to wrap it up, Fn converges pointwise on X to a measurable function f that is finite almost everywhere on X, and the limit of that sequence of integrals is the same as the integral of the limiting function f, and this value is a finite value. This completes the proof. Next, we have a proposition which says that let x and mu be a measure space and f a non-negative measurable function on X. Then there is an increasing sequence psi n of simple functions that converges pointwise to our f, and the limit of the integrals, integral of psi n over x with respect to mu, is equal to the integral of f over x with respect to mu. So all we are given here is a non-negative measurable function f. That's it. And we need to find an increasing sequence of simple functions which converges pointwise to our f, with the property that for any given point x, the limit of the sequence of integrals of these simple functions at that point is exactly equal to the integral of the given function at that point. It's a two-line proof. For the first part, we simply apply the simple approximation theorem, which for a given non-negative measurable function f ensures the existence of an increasing sequence of non-negative simple functions that would converge pointwise to our f. Furthermore, since every simple function is measurable, what we have is an increasing sequence of non-negative measurable functions, say psi n, which converges pointwise to our f for every point x in the space X. Hence, we can directly apply the monotone convergence theorem to get the last part of the result. That's it for today. Thank you so much for watching this video. I appreciate it a lot. Feel free to add your feedback in the comments. I will see you again in the next one.